So today we'll start talking about filter transformations. Then we'll move on to second order systems. And then one of my favorite topics for the course, the feedback systems. So, you know, we might go until 12:30 today, but if you hang around until 12:30, I promise you that I'll make it worthwhile for you to hang with me until the end of the feedback systems lecture. There is a This lecture is I feel very excited to deliver it, and at the end I have a video that has a demonstration to go along with the lecture itself. I hope that you hang around until the end of the lecture. We might go a little bit over in terms of the time. So we'll start with trying to wrap up the discussion on the Butterworth filters. We designed a third order Butterworth filter in the previous lecture. Now, how about if we expand that to an n or nth order Butterworth filter? The transfer function or the frequency response is going to be very similar. The form of the frequency response is going to be very similar to the one that we derived for the third order, except that instead of writing 2 times 3, we had j omega divided by j omega c, where omega c is the cutoff frequency for the Butterworth low pass filter. We raised that to the power of 6 in the previous third order Butterworth filter derivation. Now the generalized form is going to be 2n. So the magnitude squared of b of j omega, where b of j omega is the frequency response of the nth order Butterworth filter, is 1 divided by 1 plus j omega divided by j omega c. Omega is your frequency variable, omega c is your low pass filter cutoff frequency, and cap n is the order of the filter. You can see that omega c is called the cutoff frequency because if you substitute omega equals omega c, your magnitude squared of b of j omega becomes 1 over 2, which means that's the half power frequency. That's when half the power gets through the low pass filter. That's how we define cutoff frequency. It is the frequency at which half the power gets through and half the power does not get through the filter. Now, how about the poles of b of j omega squared? Well, we would just simply take the denominator, set it to 0, and in a very similar manner as we found the location of the poles for the third order filter, we find that the values of omega that make the denominator go to 0 are omega c multiplied by e to the j pi over 2 1 plus 2k plus 1 divided by n. Now in this, what does this mean? This means that all the poles are omega c away from the origin. They are on a circle with the radius omega sub c, the cutoff frequency, and the angles at which they are present is determined by increasing k from 0 to 2n minus 1, and cap n is the order of the Butterworth filter. You still have that pi over 2 factor because j is e to the j pi over 2. So you have to add 90 degrees to that angle. So all the poles are on a circle at various angles, but omega c away from the origin. So you give me the order of the filter and you give me omega c, the cutoff frequency desired for the low pass filter, I will tell you where all those poles are. Right? Now, of course, these are going to be on a circle. Half of the poles are going to be in the left half plane, half of the poles are going to be in the right half plane, because we are looking at the magnitude squared of b of j omega. The ones on the left half plane are going to be stable poles, and that's what we would consider the actual poles of the nth order Butterworth filter, so that we have all stable poles and our low pass filter is stable. Now, can we do a frequency transformation? So suppose we have designed an nth order low pass Butterworth filter. Can we transform that into a band pass filter? We can do that frequency transformation by using this particular transformation result, which is p divided by omega sub c. Omega sub c is the cutoff frequency of the prototyped low pass filter. So you are starting with a prototype low pass filter. We already have that designed. Nth order Butterworth low pass filter of a certain cutoff frequency. We already have designed that, which means that we have already figured out what is B of j omega, and we know where all the poles are located. Suppose we are already there. Now, can we transform that to get a bandpass filter which looks something like this, right? Instead of having a center frequency of 0, now it is going to be centered at some resonant frequency omega naught with a bandwidth of omega h minus omega L. So bandwidth over here, which is denoted by cap B for a bandpass filter, is omega h minus omega L, right? That's the bandwidth of the desired bandpass filter. And we get that by transforming the already designed Butterworth filter into this bandpass filter. The center frequency omega naught is essentially the geometric mean of the cutoff frequencies omega sub L and omega sub H. And the bandwidth is omega H minus omega L. So for a certain bandwidth and center frequency, we want this bandpass filter to be designed by transforming the already designed low pass filter. So how do we do this? We are going to use this result. What is in this result? How do we use this? Well, first of all, let's do the easy discussions first. The easy parts are omega naught. What is that? That is the center frequency of the desired bandpass filter. What is cap B? That is the bandwidth of the desired bandpass filter. So we know omega naught, we know B, because that's what we desire our bandpass filter to be designed for. What is omega sub C? Omega sub C is the cutoff frequency of the already designed low pass filter. So we already have the low pass filter designed for omega sub C. So that's your cutoff frequency of the low pass filter. What is S? S is the complex frequency variable for the bandpass filter. So S, think of S as the complex frequency variable for the bandpass filter, right? However, P is actually S for the prototype filter, which is the low pass filter. So think of P as, let me write it in right here. P is S for low pass filter. Now, because there is one complex variable S, and we need to differentiate between the already designed low pass filter and the desired band pass filter, we need to differentiate which complex variable we use. And to differentiate that, we are introducing two letters, P standing for prototype for the low pass filter, S standing for desired band pass filter. But they are both referring to the same complex frequency variable S, right? So it's the same variable, but we are differentiating them into two here. So let's try to take a look at what happens to the poles when you do this frequency transformation. Now, clearly, let's substitute some extreme values of P. If you substitute P equals 0 in this transformation equation, you will see that S, you will get two values for S, plus and minus j omega naught, where omega naught is your center frequency of the bandpass filter. One pole for the low pass filter gave you two poles for the bandpass filter for when P is 0. And when P is infinity, very similar thing happen. S is 0 and S is infinity. Again, you get two poles in the S plane. So if you think of P plane being for the prototype filter, one pole in the P plane or for the prototype will transform to two complex conjugate poles in the S plane. And you can actually think of it as, for the low pass filter, we are talking about P plane, and then for the band pass filter, we are talking about the S plane. One pole, one cross mark, will transform to two complex conjugate poles, as shown by this diagram. and that is essentially obtained by the transformation equation that is given in the red box. All right. So one pole going to two poles. We have seen the transformation equations that we are going to use to make a band pass filter from a low pass filter. Now the next step is to take a look at an actual example here. So we'll start off with a third order low pass filter, B of P, right? Think of P as S for the low pass filter, standing for prototype. And our cutoff frequency is 1, omega sub C is 1 for the low pass filter. And we are going to transform this into a band pass filter with the transfer function H sub BP of S with desired bandwidth of 2 and center frequency of 5. That's what we want to derive. How did we derive that equation? I can provide the explanation, but it's going to be so because of constraints of time, I'm not deriving that equation for now, but it is related to circuit elements, right? So I can derive a low pass filter by using inductors and capacitors, and then I can transition that into a band pass filter which require resonance to happen. So more L's and R's and C's, and I can using those circuit elements, I can derive that equation. So I have that derivation with me. I can upload that to the website, but it is a little bit too time consuming. So I will leave that for you guys to take a look at. All right, so let's move on here. So I want to transform this low pass filter into a band pass filter. My desired bandwidth is 2 and my desired center frequency is 5. So I'm going to make the first, let's start with the pole zero diagram of the P plane for the prototype for the low pass filter. Where are those poles located? It's a third order filter. So of course you have 3 stable poles in the left half plane. Those are located depending on what omega sub C is. In the previous lecture, we saw where those are located, right? They are located at omega C away. So it is 1 away from the origin. And they are present at angles that are 60 degrees apart. So one is at 120 degrees, one is at 180 degrees, and the last one is at 240 degrees. Right? That corresponds to having the real part of the poles as negative half and the imaginary part to be plus and minus square root 3 over 2. Right? So that's from the earlier discussion. So we have 3 poles. We have also said that each pole becomes 2 of them in the S plane. So 3 poles should become 6 poles. Now the question is, where are they in the S plane, right? So the transformation is P divided by omega C equals S squared plus omega naught squared divided by bandwidth times S. So for the given bandwidth 2 and for the given center frequency 5, omega naught squared will become 25. Your substitution is P equals S squared plus 25 divided by 2S. What are we going to do? We are going to simply substitute this P into our prototype transfer function, third order Butterworth filter. And if we do that, we are going to get the transfer function of the band pass filter to be this big polynomial in the denominator here. You have 8s cubed in the numerator. So you have a 6th order polynomial in the denominator. Now, of course, if you want to find the 6 roots of the denominator, you can do that. It's going to be probably easier for you to use a calculator or MATLAB to find the 6 roots of the denominator. That will give you the poles, the 6 poles of the bandpass filter. However, because we have the transformation formula, you can use that to find the 2 poles for each pole in the P plane. So when pole was P equals -1, where is this guy? Pole P equals -1 is right there, right? And the other 2 are, so this guy is say blue and this guy is say pink, right? So that one is at positive, so that this guy is blue. I use blue here. And then I used pink for the last one. So for each of those poles, we can use the transformation equation that we had, right, which is P equals S squared plus 25 divided by 2S, to find the two values of S in the S plane. You will see that they all appear as complex conjugates of each other. You have two poles there, you have two poles there, and you have two poles there. Now, 3 poles for the low pass filter became 6 poles for the band pass filter for the desired center frequency and bandwidth. Now let's plot them all into a pole 0 diagram. You can clearly see that those 3 became 6 of them. All of them are on the left half plane, so stable band pass filter. But if you notice, what is the center frequency? We wanted center frequency to be 5. You see this? It is now, one line. 5, -5. Right? So they're all to the left half plane, but instead of having those 3 poles like this, for the band pass filter, we had them here, right, at 0. But those moved to +5 and -5, giving you a band pass filter. And the discussion that we just had is essentially written up, and the corresponding MATLAB code is also provided. And if you want to experiment that with the MATLAB, you feel free to do that. But that's essentially how you would transform a low pass filter, Butterworth, for a particular order into a band pass filter, given the center frequency and the bandwidth of the desired band pass filter. All right. The next thing that we are going to discuss is the pole locations for second order systems. We are going to try to observe oscillations, behavior, stability behavior of second order systems in a lot of detail. That's coming up next. So we have a second order system, second order transfer function, some system whose transfer function is h of s, and we have written h of s as some numerator polynomial n of s and some denominator polynomial d of s. And it is a second order system, which means that the highest power of s in the denominator is 2. So d of s is a second order polynomial. Where are the poles? Find the roots of d of s. Where are the zeros? Find the roots of n of s, right? So d of s has 2 roots, h of s has 2 poles. That would mean that it is a second order system. Now, the general transfer function h of s for a second order system can be written in this form. What happens if it is not in this form? Well, manipulate it to get it into this form, right? You might have to multiply and divide by a certain factor. You might have to rearrange the coefficients of s. You have to manipulate things to get it into this form. The numerator is omega n squared. The denominator is a second order polynomial in s squared plus 2 zeta n, 2 zeta omega sub n s, omega n squared, where the parameters of the second order system are zeta is called the damping factor and omega n is called the natural frequency. And we will see how these factors play a role in the stability of a system. Some are going to be more stable than the others. Now, damping factor is going to be a value that could be 0 or it could be greater than 0. So 0, zeta greater than, that's it. It can be greater than 0. That's it. It can go as high as possible, right? The more you increase damping, the less amount of oscillations you will have in the system, right? So if you want to damp out all the oscillations, increase zeta. Next, if you have oscillations in your response of the system, then you will have those oscillations at some frequency, right? Omega n is the natural frequency, but with that damping, those oscillations might become might happen at a lower frequency than omega n. Omega n is the natural frequency. So what is the frequency of these oscillations if there was no damping present? But if you damp out some oscillations, then they happen at some other frequency, which we are calling as damped frequency. We'll talk about that in just a bit. this is going on. Why did this get stuck? Hmm? All right. Right now things might appear like just coming at you as parameters, but we'll put all of these together as we go through today's lecture. So two parameters for this system, zeta and omega n. Zeta is the damping factor, omega n is the natural frequency. Now, because we have a denominator polynomial written up, we can factor the denominator and find out the roots of the denominator, which will essentially give us the two poles of the second order system. The two poles will be located at negative zeta omega n plus or minus, they are complex conjugate poles, j omega n square root of 1 minus zeta squared. Now, using your factoring techniques or finding the roots of a quadratic equation, you can find the two poles of this system. We are going to take these two poles and put them on the S-plane and try to analyze what happens when you increase or decrease zeta. What happens when you increase or decrease omega n, right? So we are going to try to play with these two parameters, and we are going to see how the two poles move around in the S-plane as you do that. And if you want to analyze them in a very systematic manner, you have to hold one parameter constant and change the other, and then do the same thing for the other parameter, right? So over here what we have is we are going to plot the poles in the S-plane, right? So observe what happens as you change. So you have a S-plane over here. You have the real axis, x-axis, and you have the imaginary vertical axis. And as you change, say, omega n, right? So if you keep zeta constant and change omega n, what happens is you will move away from the origin on a line, right? And depending on which constant you use, you might be here, or you might be horizontal, or you might be lower. So that depends on the zeta. But you're holding zeta constant and you change the natural frequency, and you will move those poles, those complex conjugate poles will move away in that direction as you change omega n. How do they move? Increase omega n, they will move away from the origin. Decrease omega n, they will come closer to the origin. And how is that being analyzed? You just use these two poles, right? You fix zeta and change omega n. You see what happens to the poles, right? So you can clearly see to the real part. If you hold zeta constant and change omega n, what happens to this? If you increase omega n, you will have a more and more negative real part of S, meaning you will go further out on that line, right? So, and you can apply that same logic to the imaginary part and see what happens there. But if you hold zeta constant and change omega n, you go on lines indicated by green. And if you hold zeta constant and change omega n, you go around a circle. So if you increase omega n or decrease omega n, if you increase omega n, you will go closer to the imaginary axis. If you decrease you're changing zeta, right? So if you're holding omega n, that radius is constant. If you fix omega n, the radius of the circle is constant. As you change zeta, if you are 0, you are on. If you have no damping, then you are on the imaginary axis. As you increase zeta, you will move this way. So as you increase zeta, you will move this way. Both poles move towards the origin. Both poles move towards the real axis. And again, these conclusions are being made by observing how the poles move. Keep one parameter constant, change the other. And there is a reason why we are doing this, because this impacts our overall stability of the system. So we need to make sure how is the dependence of stability on zeta and omega n. Now on this other sketch of S plane, we have taken two poles. Those two poles are at some omega n and some zeta. Minus zeta omega n plus or minus j omega n square root of 1 minus zeta squared. Those are two general complex conjugates poles of the second order system, right? Marked here and here. The distance away from origin is omega n, the natural frequency. However, if you look at the y value for that pole, it is actually omega n square root of 1 minus zeta squared. So that is actually your damped frequency, omega sub d, right? So omega d is related to omega n. Natural frequency, the other one is damped frequency. So damped frequency is the frequency of the oscillations due to the damping of them, due to the damping of the oscillations. Next, how can I find out zeta? Well, zeta, because I know the two locations, I know the x and the y. I know the real part and the imaginary part for those poles, right? They happen at on one certain line and one red circle, because over here I'm considering zeta and omega n to be a constant, right? Cosine theta, if that is theta, cosine theta will be simply zeta. That is your damping factor. So over here we have a relationship between the angle and zeta. We also have a relationship between damped frequency and the natural frequency and damping factor zeta. So all of those are being sketched over here. Two poles, right? Are these poles stable? Well, yeah, they are on the left half plane, so they should be stable. Now let's try to see what happens when you play around with this damping factor zeta. Let's start with an undamped oscillation, undamped system. Undamped system essentially means no damping. Zeta is 0, right? And when you have zeta equals 0, the response of this system, you see this, oscillations keep going on forever. No damping, right? No reduction in the amplitude of oscillations. So if you excite this second order system with some energy, it may be a step input, it may be an impulse input, whatever input you give it, it will result in continuous oscillations that don't go away when zeta is 0. So no damping, zeta is 0, that's an undamped system, and the response will have oscillations that go on forever, right? That's an undamped system. Now, when you start increasing zeta, right? So if you have zeta, so yellow, right? So yellow is here and here. The two poles are on the imaginary axis. Now, when you start increasing zeta, you go to a underdamped case. Actually, let me use this. So between 0 and 1, not including 0 and 1, you have a underdamped system. What does that mean? This pole moves here and this pole moves here. They come very, very close to the horizontal axis, and they only meet on the horizontal axis when damping factor becomes a 1. So between 0 and 1, those two poles will travel along that dashed red line towards the horizontal axis. This guy will move here as zeta increases from 0 to 1, and this guy moves from here to here as zeta increases from 0 to 1. What is that called? It's called an underdamped system. Why is it called underdamped system? Because the impulse response of this system looks like this. There is damping, right? So as you can see, the envelope keeps going down. So it's exponentially decaying. It is damping. However, the oscillations are still there, right? So it's not like you're absolutely not seeing any oscillations. You are seeing certain oscillations, but they die out with time, right? So I hope you see that those oscillations are now, you see, this is going to be at omega n, natural frequency. No damping, those are going to be at omega n. But this one is going to be at omega d, damped frequency, because there is some damping involved. Those oscillations are going to repeat at damped frequency omega sub d. Okay, what happens next? What happens if you increase omega zeta more? If you reach the critical point, zeta equals 1, you have a critically damped system. That means both the poles, one traveled from the positive, one traveled from the negative, and they both now meet on the horizontal axis. So two poles right on top of each other or on the horizontal axis that are omega n away from the vertical axis. Those are going to be at zeta equals 1. So critically damped system there. The impulse response looks like this. So as you can see, no oscillations appear, but you still see some response, right? So there is a fast decay. There is a decay in the energy, but it goes away very quickly in that case. That's called a critically damped system. As you increase the damping factor beyond 1, this pole will move this way to the right and the other pole will move to the left. One pole will move to the right, one pole will move to the left. So both of these poles now, there is one going to the right, one going to the left. When zeta is greater than 1, that's called a overdamped system, and that leads to a slow decay. So you see this, the response is not very strong here. The amplitude of that response is much lower than the critically damped case because we have increased the damping even further, but there is a slow decay. The energy remains in the system for a lot longer. It decays out slowly. That's called a overdamped system. So to go back and take a look at this, when you have an undamped situation, your poles are both on the imaginary axis, and as you increase the damping factor, each pole moves on that circle, semicircle, to meet at the horizontal axis, the real axis. That's called the underdamped system. This is where zeta is between 0 and 1. When zeta is 1, they both poles meet on the real axis. That's when you have a critically damped situation. The response has a faster decay, no oscillations. After that, if you increase zeta even further, one pole will move to the right, the other pole will move to the left. The one that is moving to the left, it is becoming more and more stable, but the one that is moving to the right is actually moving towards the danger region, right? Because you have an unstable system if it crosses over to the right side. It will not do that, but it is moving to the red region, the danger zone. That is called the overdamped case, and that leads to a slow decay. So the amplitude, the strength of the response is not as high as the critically damped case. No oscillations because we have killed them with increasing damping, but there's a slow decay that results from this. There's a question on the chat box. This is because the imaginary portion contributes to the oscillations of the function. So imaginary portion contributes to the oscillation of the function. I'm not sure if I understand. So the imaginary portion is dependent on both zeta and omega n, and even the real part is dependent on both zeta and omega n. So I cannot say imaginary portion just is dependent on one of them, right? But if you say I will fix one and then change the other, then you can see those lines and constant circles coming in. When you change only zeta for a particular omega n, that's when your poles will start moving in that way. So one guy, so let me actually trace this, maybe in a blue, right? This guy, maybe I can use green here. This guy moves like this and this, right? And then moves like this and this, and then this guy will move like this and this, right? As you increase zeta. When it is purely imaginary, there is pure oscillation. Perfect, yes. When it is on the imaginary axis, no damping, only oscillation. The response keeps going on forever and ever and ever. We were talking about this last scene from Inception movie, right? Like the marginally stable system. That's what you have, undamped. It goes on forever, pure oscillations. All right, let's take a look at an example here. We'll start with a second order system defined by this transfer function, 100 divided by s squared plus 10s plus 100. We are going to first find damping. We are going to classify the damping: undamped, underdamped, critically damped, overdamped. Which one is it? And then we'll also try to find the inverse Laplace transform and obtain the impulse response of this system. Now, if you see this, try to compare the h of s that is given to us with the standard second order system and equate powers of s. When you do that, you will see that the natural frequency comes out as 10 and damping factor will come out as 0.5. When the damping factor is between 0 and 1, we know that that's an underdamped case. We highlighted that in blue in the previous slide. Right? So I'm going to do that. And the natural frequency over here is 10. And now because we know zeta and we know omega n, we know the two locations of the poles using the earlier result. So minus 5 plus or minus j5 square root 3. That's going to be our two poles. Will we do a plot for holding zeta constant? We are not going to do a plot for that. We just know that they will move like this. Maybe they will move outside like this. Right? The two poles will move away from that on a line. Let's see. So by comparing coefficients of the denominator, we have found zeta, we have found omega n. By observing the value of zeta, because it's between 0 and 1, we know that it's an underdamped situation, which means that there is going to be some damping, but they are going to be oscillations as well, right? And those oscillations will happen at omega n multiplied by square root of 1 minus zeta squared. So those oscillations are going to happen at damped frequency, not the natural frequency. All right, so let's take a look. Because we know the two poles from earlier, we can plot them on the S-plane. Minus 5 is the real part, which is negative zeta omega n, plus or minus j5 square root 3. That's going to be your damped frequency there. What is theta here? Cosine theta is zeta. Zeta we know is 0.5. So cosine inverse of half is 60 degrees. Right? So we know that is 60 degrees. We know. So what all do we know now? We know damping factor. We now know natural frequency, which is 10. We know damped frequency, which is 5 square root 3. Right? Because that's where this is. This lies at 5 square root 3. That's your. So if you keep going on this circle, you reach 10. but the y value for that particular pole is damped frequency 5 square root 3, or the imaginary part of both poles. So we have sketched the pole zero plot for the second order system here. We still need to find the impulse response, which means that we need to find the inverse Laplace of h of s. So in order to find the inverse Laplace, for this particular system, we can actually use the Laplace transform pair that is provided in the Laplace tables, which is omega naught divided by s plus alpha squared plus omega naught squared. The inverse Laplace transform of that is e to the minus alpha t sine omega naught t u of t. So by by writing this guy into this form, we find out that alpha comes out to be 5 and omega naught comes out to be 5 square root 3. Then using this inverse Laplace transform pair, we can write h of t, the impulse response, to be 20 divided by square root 3. That is just a scaling factor. You have e to the negative 5t. E to the negative 5t is the damping, right? That's the rate at which the oscillations are dying out. But the oscillations themselves are happening at the frequency omega sub d, which is 5 square root 3 in this case. So you have an impulse response that looks something like this. It goes down based on the exponential decay, but those oscillations happen because of the sine factor there. Right, so the oscillations are repeating at 5 square root 3, and the damping is happening at the rate of 5. Alpha is 5. All right, questions about this example? Given an h of s, second order transfer function, how do you find the pole zero plot? How do you find zeta, omega n, omega d? How do you classify the system into undamped, underdamped, critically damped, overdamped system? And for a given classification, how does the response look like, right? Does it have oscillations? Does it not have oscillations? Does those oscillations die out, or they never die out? So those are the things that we are talking about here. Okay, now the next thing that we are going to talk about is certain parameters of a second order system for a step response. So this same second order system, if it was excited by a unit step, it would have a step response. And the step response, clearly, you see, if I do this, if you have a system here, you have h of s, a second order system, you are giving it an input of a step, which means that, right? The output, even if it has some damping or it has some oscillations, how would it look like? It would look like something like this, right? It would have some zero. So no energy for time zero, no output. But when you give it energy, it might go up and then settle down, right, to 1. If this is 1, that is 1, right? So the response of this second order system, when you give it a unit step, might look something like this. So it overshoots and then it slowly settles down to 1, right? So that's a example of a second order system whose transfer function is defined as h of s, a second order polynomial in the denominator. So for this kind of response, we can find a few parameters. This is for an underdamped case only. So there is damping going on, and there are some oscillations going on as well. So the response that we just sketched earlier is sketched again over here, right? So it starts at 0, overshoots, and then the oscillations also have a decay going on as well. So for this kind of a response, we can find a few parameters. The derivations of these parameters is provided. However, my goal is to just walk you through how we are deriving it, not as much as all the details of the derivation. I will just talk about uh, how we did the math, not as much as walk you through the math completely. One is the rise time. The first parameter is the rise time, which is how much time does it take for the response to go from 10% of the final value to 90% of the final value, which if this is the final value, y final, right, that's the value of the response at to which the y of t settles, right, the step response settles to that value in the steady state finally. So that's final. So so it starts at 0. How much time does it take to go from 10% to 90%? That's called rise time, and we'll see how we can derive that in just a bit. Next is the peak time. What is peak time? Peak time is time at which you have the maximum value in the response. So time at which your step response overshoots, and then you have the high peak there. What is the time at which that high peak happens? That's your peak time. That's actually pretty easy to calculate because all you have to do is differentiate the step response, equate it to 0, and the first time the slope becomes 0 is your peak time. Right? Next is your settling time. For settling time, TS, it is going to be the time at which your response goes as small as plus or minus 2% of the final value, right? After that, your response should not go beyond the 2% of final value. That's your settling time. Percentage overshoot. Percentage overshoot is the maximum y max, which is the value at peak time, minus the final settling value for the response divided by the percentage of, so expressed as a percentage of the final value. So y max minus y final divided by y final, expressed as a percentage. That is the percentage overshoot. So for percentage overshoot, we need y final and y max. That's your overshoot. Let's try to derive a few of these guys. So the basic equations for underdamped second order system are provided over here. Here you have the step response. So all we did is take the transfer function and treat this as step response. Okay, how do we take h of s and make it into step response? Suppose you have transfer function. How do I find y step of s? This goes back to the relationship between impulse response and step response. What is the relationship between impulse response and step response? Differentiate, yes. When you differentiate step response, you get impulse response, right? So when you're differentiating in the time domain, you're dividing by s in the Laplace domain. So you took h of s from before and you divided it by s, you got y step of s. Let me erase all of this. That essentially, that s is what is making it the step response instead of h of s. Now we'll substitute natural frequency of 1. Our step response in the Laplace domain becomes this. And using MATLAB, we can actually sketch out all these functions in the inverse Laplace of these functions, the response, right? So response is being sketched by finding the inverse of this. Step response is the inverse Laplace of y step of s. If you find the inverse Laplace of that and sketch it for various values of damping factor, you can see that the lower the damping, the more the overshoot, and you have a that decay is much steeper. So this guy is going all the way up, right? The overshoot is low. But if you damp things more, right, zeta equals 0.8, that overshoot has come down drastically. So you see the response in this system as you change zeta. And the code for sketching it is written on the right here. Also, using the inverse Laplace techniques, all the work is not being shown here, but using the inverse Laplace techniques, if you find y step of t, that is also written over here. This equals inverse Laplace of y step of s. So a pretty complicated equation. We are not going to derive that. We are just simply going to observe how the damping factor and natural frequency are playing a role in this. For now, we are looking at the effect of the damping factor. As you increase the damping factor, your overshoot goes down, right? Essentially, that's what it is. Next, we are going to try to find TP, the peak time. How do you find the peak time? Well, take your step response in time domain, differentiate it with respect to time, equate it to 0. When you equate it to 0, you find the point at which you get the peak, right? And the first value of time that makes it 0, the first peak, is going to occur when t is that pi divided by omega n multiplied by 1 minus zeta squared, or simply pi divided by omega d. So the derivation is provided over here, but as a summary, I'm providing the explanation of how the math would flow. You would take the step response, you would differentiate it with respect to time, and you would equate it to 0. And the first value of time that makes that happen is going to be your peak time. So we are going to use this result. Next, we look at the percentage overshoot. Percentage overshoot is defined by this equation: y max minus y final divided by y final. So y final is 1, right? If you have a step response, eventually your output will settle down to 1. So y final is 1. We already know that. We need to find y max. What is y max? Y max is the step response value at peak time. So we will evaluate the step response at TP. We already know TP as this from earlier. So we will substitute TP into step response, evaluate y max, plug it into our percentage overshoot equation to evaluate this as 100 times e raised to e to the negative zeta pi divided by omega d. Sorry, not omega d. It is just the square root of 1 minus zeta squared. So another result for percentage overshoot. The below sketch is showing you the percentage overshoot as you change zeta. We have already seen that if you increase zeta, the percentage overshoot should go down. And this plot essentially shows that it goes down exponentially, right? So as you change zeta, if you increase zeta from 0 to 1, your percentage overshoot goes from 100% all the way down to 0%. Okay, let's move on here. Next is settling time. Settling time is the time at which your response reaches plus or minus 2% of your final value, right? So after that, it will remain in that those two bounds, which is plus or minus 2% of the final value. So which essentially means that it will stay within those two lines, plus or minus 2% after settling time. So for this, we are going to use a slightly different trick. What we are going to do is, instead of taking a look at oscillations, we will take a look at the envelope of those oscillations. And you will see that the envelope actually is an exponential envelope here. And that is given by this equation here. Y envelope of t is this particular exponential decay. So instead of taking a look at 2% of the actual the actual step response, I will instead, as an approximation, use the envelope and then evaluate 2% of the envelope and then find the time for that. So an approximation is being used here. So 2% of the envelope as opposed to the oscillating behavior. We know the time, we are trying to find the time at which this is 2%. So we know y envelope of t, we are trying to find ts at which this becomes 0.2. You will see that the time ts that satisfies this equation is given by negative natural log of 0.02 square root of 1 minus sigma squared divided by zeta omega n. That is the exact value of settling time. But if you go down and observe settling time as a function of zeta, you will see that this equation, the numerator of this equation, can be approximated to 4. So we are going to use this equation as an approximation of settling time, 4 divided by zeta omega n. So lots of equations, some ideas about how to derive them. You are not expected to derive these things, but at least you should know where they are coming from, like how the derivation steps are being done, and more importantly, how these parameters, 4 of them, right? If I go back, there are 4 parameters. So rise time, peak time, settling time, and percentage overshoot play a role in the response of this system. So for a particular, for a desired response, you might have to adjust what zeta, what omega n, and how rise time and peak time and settling time and percentage overshoot correspond to those zetas and omega n's. Okay, let's move on here to feedback system. So what I'm going to do is stop recording